Okay, well, good afternoon. Welcome to the Speak Out for Engineering Europe Regional Final 2020. My name is Chema Garteiz. I'm the current treasurer of the IMechE Iberia group, and I will be your host during this competition. As you are all aware by now, the SOFE, or Speak Out for Engineering, is a competition for young engineers designed to help develop verbal and visual communication in explaining technical mechanical engineering related subjects. Due to the COVID-19 outbreak, the institution has implemented measures to mitigate the impact on our members, volunteers, and staff around the world, and hence, all remaining 2020 SOFE competition heats have been moved to a virtual platform. Competitors have been briefed about the rules, and they have sent us a 15 to 20 minutes pre-recorded presentation on a mechanical engineering subject. After this presentation, there will be a 10 minutes live discussion and questions from the judges. 90% of the total marks are given for the presentation skills, with only 10% for technical content. Prizes will be awarded to first and second places, with £300 and £200 respectively. The decision of the judges on the award of the prizes shall be final. These prizes are funded from the institution's Trust for Educational and Research. This year we have 4 participants. We have Thomas Brown, who's coming from Scandinavia, Nassar from Palestine, Nicolas Sammut from Malta, and Guillermo Muñoz from Spain. The competition will be launched in 10 minutes with our first 2 contestants. Then we will have a 10-minute break for a coffee or a tea, and we will proceed with our last 2 contestants after that break. At around 5 o'clock, the panel of judges will have a 30 minutes break to deliberate, and the results will be announced by 5:30. Let me now introduce our judges briefly. Our chief judge for the day is Raymond Hodgkinson. Our next judge will be Farah Bask, and Daniel Fantoni as our third judge. In case that any of the participants have a draw, they have equal number of points, it will be up to the chief judge to decide which one will be the winner. As a reminder, I would like you to switch off all your cameras and microphones during the competition. I think we have time for a brief introduction to our judges, so let me introduce you to Raymond Hodgkinson. Hello, Raymond. How are you?
I'm well, thank you. Sorry, I obeyed to switch off. Hi.
Raymond, I know you have been a judge of the SOFE for a couple of times, at least. So tell us a little bit about your background, where you come from, and why you are the chief judge for this competition as well.
By background, I've been a member of the IMechE since 1967, a fellow more recently, but for quite a few years, and international trustee, in fact, international vice president. I have, until very, very recently, chaired the International Strategy Board, having, before that, worked in both Germany and Europe as IMechE representative. Why I'm chief judge is because Adam kindly named me chief judge. That's all I know on that.
Okay, excellent. I don't know if Farah is with us at the moment. Farah, are you here with us?
I am here.
Yes, excellent. So Farah, I believe this is your first time as a judge in this competition?
It is my first time as a judge, and I'm honored to be a judge. I've been with the IMechE now 8 years, and my role is the Global Relationship Manager, and I work with industry, academia, organizations, students and apprentices, all to enable them to become professionally registered. So I guide them through the process. I'm lucky enough to work with some interesting global companies, your JCBs, your WSPs, BP, Shell, etc. So very, very wide-ranging industries. And my background before being at the IMechE was that I actually lived in Sweden for 13 years, and I was involved in plate type heat exchangers. I was a sales engineer for Spirax Sarco, selling steam equipment, and I had my own company in terms of control systems. So yeah, so that's a little bit about myself, and I look forward to the presentations today.
Excellent. Thank you very much, Farah. And our third judge is Daniel Fantoni. Hello, Daniel.
Hello. Hello, everyone. Nice to meet everyone and speak to everyone. What would you like to meet? What's your question?
Well, I know that you have been in the SOFE a couple of years ago.
Yes, I've been fortunate. I've been participant to a few SOFE events. There was one in Malaysia, I think it was 3 years ago, one in India, one in the UK, and 2, or was it 3 years ago, we held the event in Italy, and I was the judge for that with Raymond and an external person. So it's always an interesting event. Always learn something new, and it's nice to meet youngsters and see their enthusiasm and their particular view. So in Italy, I'm the chair of the IMechE group. We tried to have a SOFE this year, but COVID got the better of us, unfortunately. And so that'll happen next year, hopefully.
Okay, in this occasion, the SOFE will be virtual. So that means that we have pre-recorded presentations. However, the 10 minutes about questions are going to be live. From your point of view, Raymond, Farah, or Daniel, what do the contestants have to expect from your questions?
Daniel?
I think they've just got to be relaxed about the questions. We're not going to be questioning them to put them in difficulty. The idea is that we will be asking the questions if we think there's something they might have added and they perhaps forgot or didn't. We're trying to help them perhaps to complete the explanation of their chosen topics. So we're not trying to put in any trick questions. That's not the point.
I agree with that totally. We're there to get, let's say, it's the sort of questions you would expect if you'd given a lecture at a public event and then asked for questions. So people wanted to understand a bit more about your topic or about yourself.
Yes, we're not trying to catch them out. We're not going to be asking a question and judging them on the correctness of the response. It's more how they reply and how they complete the information or the things we're suggesting.
Excellent, because I know that when they ask you questions, people tend to be very, not afraid, but at least nervous. And in these occasions, since this is going to be something virtual, we don't know what to expect. But as you have said, yes, be relaxed and just answer the question the best you can, because you know about the topic.
Exactly.
Excellent. So we have 5 more minutes before the start of the official competition. I don't know if anybody has any doubts about the competition. Any of the participants has any questions before we start? You have all been briefed on the rules. You have presented your pre-recorded presentations. Still, do you have any questions beforehand?
Can you just repeat the name of the Malta participant, because it's not written down on my...
Nicholas.
Hi, I'm over here.
Nicholas Sammut.
Yes, Sammut.
Thank you.
Welcome, no problem.
So it will be Thomas from Scandinavia. Then it will be Nassar from Palestine. Then it will be Nicholas from Malta after the break. And finally, it would be Guillermo from Spain.
One question from me. I notice your internet connection is not very effective because you're coming over your picture's coming over very kind of on off. I'm just wondering whether you're running the presentations from there and whether that might present a problem.
No, it's Adam who will be running the presentations.
Okay, good. Okay, I'm sure you're confident then.
Yes.
Okay.
Okay, before the presentations, each participant will have a 1 minute pitch to talk about whatever they want to talk about. Maybe they want to introduce themselves, tell us about the reasons why they are doing this presentation. So, Adam, do you think we should wait for 3 minutes so we make everything official, or should we start?
I think we can just get started now.
Okay. So our participants, as I have said, they will have 1 minute pitching session before their presentation. Please let us welcome in first place Thomas Brown. Thomas.
Hello. Thank you for coming to listen to my presentation today. I'll be talking about closing experience gaps with Rheology. The rest of the pitch is included in the presentation, so I won't get into any more, other than saying that based in Scandinavia, living and working in Norway, but British by nationality. So I think that's all I need to say, and I'll pass over to the video.
Okay, thank you very much. If you can all switch off your cameras and microphones so the connection might improve a little bit. Adam, all yours. Thomas Brown, closing experience gaps with Rheology. Closing experience gaps with Rheology, Thomas Brown.
Sorry, is it only me that's not getting any audio here?
There's no sound,
Yeah.
yes.
No, that's what I was going to ask Adam.
It's not working.
When you share your desktop, you have to press share audio, I believe, and then you'll get the audio from the video. So if you stop sharing and then reshare, but enable audio.
Do exactly what you did yesterday in the trial run.
Let's try again.
Hello, my name is Thomas Brown, and today I'm going to be giving my Speak Out for Engineering presentation.
Is it working?
Yes.
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 Oh,
Good.
On the subject of closing experience gaps with Rheology. So an introduction. Who am I? I got my degree in mechanical engineering at Bristol University in the UK and the University of Illinois in the USA. And I'm a chartered engineer with the Institute of Mechanical Engineers. And I'm currently Norway based. I work in the oil and gas industry. My employer is Aker BP, and my position is the IMR projects lead. And what that means is inspection, maintenance and repair of subsea equipment. What do I do? So on the right, you see some of the images of where I work. So at the top is the Valhall field. In the middle is an image taken 400 meters below the sea, doing some open heart surgery on a subsea Christmas tree. And you can see an operation taking place with ultra high pressure water, 2000 bar, with a couple of ROV manipulators in the screenshot. And at the bottom is a piece of technology we use, a video we've taken to get essentially a computer model from videos and still images taken by ROV subsea, and then that still model can be used to take dimensions off to do retrofit or retrospective engineering on designs. In other words, we're using cutting-edge technology, we're solving complex problems, and using robotics to produce and maintain safe and efficient oil and gas production from beneath the sea. And whilst there's a need for oil and gas in the world, I'm pleased to be working in Norway, which has some of the highest standards of quality, HSE, and pollution control in the world. So, what are my personal improvement goals? I want to improve or increase the amount of first-hand design work that I'm doing and the amount of first-hand practical work that I'm doing. If you look at the images at the bottom of the screen, I'm doing a lot of what's on the left, so a lot of work in the office, but less design and less fabrication than I would like. So, closing the gaps. At the moment, my skill set is well represented by the area shown in red. So I've got a good breadth of knowledge and experience in planning, in the commercial and the communication and management side of the business, but less in the design and a lot less in the fabrication area. And what I would like to do is to bring those design and fabrication circles to intersect with the rest of my experience. So what opportunities have I got for solving that? Community college, potentially, but there's none in my area that would help me close these gaps. Via my employer. But no, my employer isn't in the line of business where we're doing design and fabrication on a routine basis. We're subcontracting that out and then managing those subcontractors. Private projects, potentially, yes. And with those private projects, I hope I could achieve this scenario where I'm fulfilling the core disciplines of engineering with the area represented there in green. And obviously, safety is inherent in all those points that are shown there on the screen. So, inspiration to close these gaps. I was at the Greenwich Royal Observatory in the UK some years ago, and they've got an excellent section on mechanical timepieces. And I was at the Spiegelklok Museum in the Netherlands. They have an excellent display of mechanical music machines as well as clocks as well. And with that inspiration, I started following up projects on YouTube. Some of my favorite presenters are shown here, namely Clickspring, Wintergarten, and This Old Tony. And whilst these presenters aren't mechanical engineers by trade, they display many of the traits of a good mechanical engineer, and especially a desire to learn. And what I've taken from the videos that they've put online is upskilling, so learning from what they've done and being able to use those skills that they've taught in my own personal projects. And I believe that Rheology is an excellent hobby in which I can use to close the experience gaps that I showed you earlier. You can define Rheology as the art of creating mechanical timepieces. In terms of the pros, if you follow up this hobby, you can have relatively modest workshop space requirements. It's not massive machines you're using. There's a requirement for high levels of dimensional precision and quality. So there's a high surface finish you're looking for, and you're working to dimensions typically a thousandth of an inch or 0.025 millimeters. And the finished product is a mixture of both engineering and art, and success is demonstrated by a high quality finished project, which has high timekeeping accuracy. In terms of the cons, you do need quite a few machines and quite a lot of tooling, so that comes with it a cost and space penalty. And the dimensions that you work to in horological projects are typically imperial, so the plans or the guides that you find in books and all the tools that you need end up being imperial, which is different to the metric system that I've been educated on. So there's certainly a learning requirement there. In terms of minimum tooling requirements to follow up a project like this, you need a lathe, you need a milling machine complete with dividing head, hand tools, and metrology equipment. I'm showing a selection of the metrology equipment there on that image on the right. And obviously, all these things don't always come cheap. So there's quite a lot of financial outlay required to get you out of the starting blocks on this project. That's another one of the cons. What are the key skills that you need? First and foremost, you need patience. You can spend days and days working on the smallest of components, taking it from raw stock down to a finished component with high precision and, as I said, high surface finish. You need a requirement for technical drawing skills, both creating your own drawings and interpreting other people's drawings. You need a solid background in mathematics, physics, and engineering, as well as an understanding or a good understanding of machine tool operation, obviously where safety is paramount. You need to be skilled with hand tools and manual techniques such as riveting, broaching, and filing, and you need to be skilled up in heat treatment. In terms of selecting a project, I was browsing through a book on skeleton clocks and I saw a fantastic timepiece, an epicyclic skeleton clock that was designed by a gentleman called William Strutt in around the 1820s. He was a civil engineer and a member of the Royal Society. One of his famous quotes was he wasn't that keen on documenting his previous projects as he was much more keen on getting on to solve future projects and new problems. So while some of his clocks remain, there was no plans or documentation on how they were designed and their dimensions. So some retrospective engineering was performed by Bill Smith around the year 2000, and he produced a set of plans to cover William Strutt's clock from the 1820s. And I've came across those plans and based my project around it. It's a fascinating timepiece. It's got an 8-day runtime, a spring-driven fusee, a Ferguson mechanical paradox motion work, and a stop work mechanism as well. So, some of the project. First, I take a quick look at the frames here, which involved essentially laying out the design in CAD, transferring that across to brass plates, locking them together, and then removing the material outside of the line, and then bringing it down to the line and imparting a high-quality surface finish, which is what's shown on some of the images there. Obviously, significant material wastage in this process, but that material is all transferred to the scrap bin and used elsewhere on this project and in other potential future projects. Next up, the ring wheel. So cutting a traditional wheel on a home workshop is a reasonable challenge, but it's very rare to cut the inside of an epicyclic wheel in the home workshop. The image on the left shows my lathe set up for this operation. So essentially a dividing head mounted onto the lathe with the workpiece, and then two saddles mounted in tandem, locked together with an auxiliary motor turning a fly cutter. And you can see that fly cutter turning under hand power on the bottom right video on this page. Once the whole system's up and running, you feed the fly cutter into the workpiece, withdraw it, index the head round to give you the desired number of teeth, and repeat the process. Moving on, more images of the wheels and pinions. On the top left, you see the epicyclic wheel, the ring wheel. In the center, you see some of the pinions. Moving towards the wheel that's been marked out on the crossing out jig, ready to have the material removed according to the crossing out that's been done. And on the far right, you see the finished wheel mounted, ready for use. Down at the bottom, you see a few videos. You can see the teeth getting cut on the great wheel, sped up in this instance. And in the center is an interesting video. This is meshing the gears on a depthing jig, where you slowly bring the gears into a deeper mesh. And then when you've found the optimal meshing, so the least rolling resistance, you transfer the distance between the two, between the wheel and the pinion onto the plates, so that you then have the optimal separation of the wheels on your clock. You'll hear me talking about wheels and pinions. In Rheology, a wheel has typically got greater than or equal to 20 teeth, and a pinion will have less than 20 teeth. Onto the anchor escapement. So using the Lorry-Penman method for marking it out, you see some of the key dimensions shown on the top left, and then the design being sketched out onto the steel using die-chem, and then chain drilling operation to take away the excess material. And once the material's been removed and the anchor's polished, you can see it oscillating backwards and forwards on the escape wheel. On the far right, you see the final product, which has been polished and heat treated so that it's glass hard and ready for a long service life with very limited wear. Moving on, designing the hands in CAD, transferring that design onto steel plate, cutting out the steel plate by hand, polishing it, and then heat treating it so that you give it the traditional blue color. That's quite a fine process, especially on a long, thin component, to achieve the same consistent level of bluing along its length. So it took quite a few attempts to get a nice surface finish. And on the right-hand side, you see the finished hands, both the hour and the minute, that have been nicely blued. The dial, it's obviously an operation that's conducted both on the lathe and on the milling machine to create this. Quite a lot of material removal to achieve it, and soldering process to lock the cut numerals onto the dial material. The pendulum bob. So traditionally on the lathe, you're either feeding in X or Z at any one point in time, but the pendulum bob typically has a nice curved surface on it, and to achieve such a surface I had to learn a new skill, which was graving, which is essentially turning metal by hand. And once you've achieved the rough profile, then it's a sanding and polishing operation to impart a mirror finish. Once that's been achieved on one side, then it's cutting the workpiece off, turning it around on a mandrel, and then repeating on the opposite side until you're left with a traditional pendulum bob and a rod as well. Moving on to the fusee. So this is a spring-driven clock, and as the spring winds down, it reduces the force that can be applied. So what that would mean is your torque being delivered through the drivetrain of the clock would decrease as the spring winds down. The fusee tries to compensate for that. So a wire is wrapped off the spring and around the fusee, which is shown at the bottom middle of this slide. And when the spring is fully wound, the wire is getting pulled off the fusee on the smallest radius, so delivering less torque. As the spring unwinds, more wire is pulled off the fusee until at the end of the spring unwinding process, you're coming off the largest diameter of the fusee. And this fusee is shaped with a curve here in order to approximate a consistent level of torque being applied through the drivetrain of the clock as the spring goes through its fully wound state until it's in its more unwound state. Quite a tricky operation to thread on a curved surface on a manual lathe, so that was a skill that needed to be learnt for this operation. And on the bottom right, you see the fusee mounted on the great wheel with its ratchet in operation. And then this is the finished clock. So approximately 500 hours of work went into this. It would undoubtedly be quicker second time around because I've learnt many lessons along the way. And whilst your finished product is a clock, you need a lot of custom-made tooling and a lot of custom-made jigs to create the clock. If I was to build a second one, all that tooling and jig work has already been completed, so there is a potential for significant time savings if it was ever to be a repeat project. What about my learnings? So a couple of famous phrases up at the top: measure twice and cut once. It's a rule I live by. It doesn't always work. Sometimes I wish I've measured 3 times and cut once, but certainly a good rule to follow. And buy cheap, buy twice. So on a project like this, it's so helpful to have high quality tooling. And by high quality, I don't necessarily mean new. You can often get high quality at cheap by buying compared to avoid distractions, but I'm pleased at the object. If I hadn't, I wouldn't be able to you. But on this video where I was on making it and I was on the machine that was taking and the video smoothly and quickly out of sequence, watched closely, tried to X the wheel down before you withdraw the cut. What that meant was scrapping it to the entire wheel. So not getting this positive verification. On the bottom right, see it said mate the best part to the specification, and then the next heat treatment gives them the heat treatment started, and they went straight from this color to cherry red. They would not take on the desired oxide. And after thinking about it, I realized that I was using the wrong type of steel. I believe it had too much chromium content in it, and it wouldn't take on the right color. If I had done some testing with regards to the bluing before I'd started manufacturing, I wouldn't have wasted my time making these from the wrong material. So in the future, if I'm doing heat treatment on a component, I'll always test that up front to make sure it behaves like I expect it. There's a variety for second-hand materials. A lot of my tooling from car boots, from steam auto jumbles, and then so I've got mouse or at the back of this magazines. Period of projects. I mean, the a bit of a challenge to it. It's very nice, and working with the clock, it's quite pleased. In conclusion, using my improvement gaps, I've completely skeleton along the bottom of the nice various components during the fabric. You can see it's time lapse. Yeah, holds excellent within a minute. Start how series worked and get that better as I actually going forward. This project, put my gaps in that die, and I'm achieving the green area at the center now. What does the future hold? Well, potentially designing a clock from scratch and then fabricating it according to my own plans. But certainly Rheology will be remaining a hobby and a passion of mine. It really is a good challenge that I enjoy. So with that, I'll say thank you very much for listening to my presentation today. And I look forward to trying to answer any questions that you've got. Thank you.
Thank you very much.
Thank you.
Thanks.
And now we go on to the questions and answers. I believe that we have had some audio degradation during the speech, but most of it, I think we were able to listen to correctly. Back to you, Raymond. Any questions?
Yes, one question. When you cut the dial, you cut the figures separately and then soldered them in. With the tools you have, could you not have cut the dial with the figures already incorporated?
So you've identified one of my areas where I need to own up. So there's a few components of the clock that I didn't manufacture, specifically the steel wire and the numerals. The numerals were bought separately, and I soldered them in. I could have done it, but it was a time-saving activity. So to give you a bit of context on that, as I said at the beginning, I'm Norway-based, but my workshop and my tools are based in the UK. So approximately once a month or once every second month. I get a long weekend at home, and I spend that time in the workshop more or less exclusively. So I was probably looking at another couple of months of clock time to get those numerals done. So I'm afraid I took the shortcut.
Fair enough. Thank you.
Okay. You talked about some problems you had with some of the materials, but in general, were you using traditional materials for clocks? And can you tell us about the selection and whether there could be opportunities for using novel or new types of materials, perhaps in or
Yeah, that's a good question. So the majority of the clock is made of brass. Leaded brass as well for reducing friction, I understand. They typically a wheel will be made of steel, so that you avoid any galling processes. In terms of novel materials, from a metallurgical perspective, I don't think so. I've followed a little bit on the internet, and I see that some people are interested in 3D printing in plastics. But then it becomes more of, I believe, more of a CAD project. The skill then is in the design, and then it's passing it across to a 3D printer to do the manufacturing. And it's an equally set of valid skills, but the passion for me is using the mill and the lathe to do it. So it would be going down a different route. I haven't really thought of any other significant changes I could do on the material front, but if you've got some ideas, and
gold
to discuss. Ooh, gold. Yeah, well, that's interesting. So obviously the brass over time will take on a nasty tarnish if it's not treated. So I've given it all a brass treatment compound in order to retain the same bright finish that you get after the sanding with 2000 grit. But some people do, rather than a polishing compound, they do gold plating of the frames potentially in terms of leaf, or they put on some sort of surface treatment via an electrolysis type of bath. But I didn't go down that route. I'm hopefully relying on the polish to give it the crystalline surface to stop the tarnishing.
Okay, thank you.
I'll ask a question. So really interesting, Thomas, thinking outside the box,
Thank you.
using different ways of developing your experience. And I guess I wanted to really know how far have you come on this journey? What are you expecting from these new skills, and how can you develop in your current organization using these new skills? And maybe even think of within the organization, actually, this is a great way of thinking out of the box and learning something quite different and using it.
I'll try and answer those. I got a basic understanding of machine tools at high school. Then there was a long period of my life that I wasn't following up, and then I've started on some projects recently, the most recent of which is the one that's shown here. In terms of how it's helped me in my actual career, as I said at the beginning, I'm a subsea engineer, and actually last year we were working on a big project subsea and piece of equipment failure. A lot of steel that was bent out of shape and corroded and needed to be fixed. And we ended up, well, I say we, the royal we, the subcontractor that we work with ended up developing a subsea milling machine in order to be taken down by ROV and then mill away material to release some stuck components and return a system to operation. But certainly with the skills that I've learned on this in terms of cutting speeds and feeds on the milling machine, I was in a much better position to ask pertinent questions into the control system of the systems we were using at work to make sure that they were thinking of the right parameters to put into the control system so that the chatter and vibration and cutter damage was minimized as far as possible. So it has paid back somewhat in my work life as well, and I hope more opportunities will come up in the future where I can deploy some of the skills that I've learned in this private project into work.
Thank you.
Yes, in the introduction, Thomas, you mentioned safety aspects, one of the things you want to investigate. So what did you learn about safety whilst conducting what some operations obviously can be dangerous. You could have cut yourself. Maybe you did. What can you tell us about safety?
Yeah, I've had safety drilled into me from my employer. I used to work for BP and then Aker BP, and the BP lived by health and safety, and I've taken that into this project. So wearing PPE all times, so eye protection being the most important for me, as well as gloves. I feel a little bit embarrassed in some of the pictures and videos in this because you see my hands touching components without gloves, but I guess my response to that is it's not during a machining operation, it's after, it's all off the machine and at that point in time. But essentially eye protection being paramount, face protection if you're using fly cutters and so on, gloves, as well as breathing protection. So a number of the projects, when you're turning and milling, you're not only creating brass chips, you're creating brass dust. You don't want that in your lungs. So working in a closed workshop without a good HVAC system, then I've been using the same face masks that builders would wear when they're doing construction or demolition, and trying to protect the lungs as well. So not only the obvious threats, but trying to think outside of the box for the others. And some of the chemicals you're using as well, acetone to break superglue bonds, obviously highly harmful to skin, and the potential of also destroying the plastic gloves that you wear. So getting the right PPE for the job as well.
Thank you. Have you gone into trying to design any parts for yourself, or were they all standard designs?
So I've customized some of the designs where I think they weren't as attractive as they could have been, or the functionality could have been improved. But essentially, it's per plans with some tweaks and modifications where appropriate. As I tried to touch upon at the end, I want to end up designing my own clock in terms of the frame and the drivetrain. I'm not on that yet. Since I've made this, well, not since I've made the presentation, but since I finished that clock, I'm actually on a second clock. It's a grasshopper design, so a very different type of escapement. But in the medium term, once I have a couple more projects under my belt, then I hope I have sufficient experience to really go in from scratch and design the whole lot. But I'm not quite there yet. Got plenty of books to read before that's on the cards.
Thank you.
Okay, how much did you learn about different types of escapement while you've been doing these projects?
So I've only been using the anchor recoil escapement. What's interesting is it's quite the amount of precision you need to get the right shape. I was surprised that just using filing techniques, manual filing, within a day of creating the anchor, I've got it oscillating as it should. So that was a big surprise. As I mentioned, the next clock I'm working on has got the grasshopper escape. So similar design to Mr. Harrison's H clocks from the challenge he did, and I think that's going to be a much greater challenge to get that running in a satisfactory way. The grasshopper design is much more sensitive for setup, so I'm anticipating quite a lot of work needing to go into that to make it run properly.
Okay, good luck.
Thank you.
Farah, any more questions from you?
No, not from me, thank you.
Okay, Daniel?
No, I think that's fine.
Then thank you very much,
you.
Thomas.
Thank you very much. Good questions.
Thank you. Thank you, Thomas. Well done.
Thank you all. We move on to our next contestant. Let's welcome Nassar Awakde. Hello, Nassar. Nassar, are you here with us?
Yes, can you hear me?
Yes,
now.
excellent.
All right.
Hello. Well,
Hello.
you have one minute for pitching session. You can tell us anything you want to about yourself or your presentation.
So, my name is Nizar Awaude. That's the correct pronunciation, if anyone was wondering. And my presentation was regarding materials engineering and material science, specifically ceramic materials and advanced ceramics. I do not have any practical knowledge in the field, as I am still a student in my 4th year of study. However, I do find this field very interesting, possibly a specialization for me in the future. I do have a quick pitch also in the presentation itself, so I think this would be enough for now.
Okay, thank you very much, Nassar. Sorry if my pronunciation is not as good as yours. So we move on to Nassar Awaude, Advanced Ceramics, Nassar Awaude.
I think there's the same audio issue where the share has to be unmuted.
Don't worry, Adam will fix it. So just let him, we'll give him some time.
Hello, everyone. My name is Nizar Awaude. I'm a mechanical engineering student from Palestine in my 4th year of study in Birzeit University. And here is a recorded presentation about the chosen topic, which was advanced ceramics. Now, to give you a quick walkthrough of the presentation with the table of contents, I will first be talking about ceramics in general and what are the basic definitions that a material would have to adhere to be called a ceramic material. Then I'll be talking about processing of these materials in a traditional sense and what the basic process would go like. Then I would reach more advanced processes and more advanced ceramics, which is the main topic of the presentation. And then I will highlight 2 specific applications regarding advanced ceramics in the real world, in industries, in modern industries. And then I'll be presenting a more exciting side of this topic, which is the future of the field, where I'll be discussing quickly 2 research papers which have been published very recently during this year, 2020, regarding 2 specific fields of study regarding advanced ceramic materials. And so why did I choose this topic specifically? Well, myself, I'm an automotive enthusiast, and I have noticed that there have been many and various different cases where ceramic materials can be used in the automotive industry. And so that made the topic very straightforward for me to research and present, hopefully. So what are the basic definitions of a ceramic material? Well, a ceramic material is inorganic and non-metallic. I say non-metallic, well, the finished ceramic material exhibits non-metallic properties. However, it might contain metals inside the composition of that ceramic material. Now, these metals and non-metals which make up the composition of the material would be bonded chemically through ionic and covalent bonds. And that is important later on when I discuss the properties of ceramic materials. So here we see how they depart from metals in being hard and brittle, compared to metals which are ductile. And that can be useful in whatever specific case where hardness and brittleness is desired or required. They're also great insulators. They're great thermal and electromagnetic insulators, and that is due to their chemical bonds, which do not allow largely the movement of free electrons, which reduces greatly conductivity. They're also very chemically stable due to those chemical bonds. They're also physically wear resistant and very durable. And that is due to their crystalline structure, which is very strong. Now here, a traditional process of how a ceramic material might traditionally be manufactured. Well, it starts off with the raw materials, which are usually found in powder form. These raw powders are then maybe mixed with additives, depending on our specific situation and any desired properties that we need from those additives. And then when the additives are mixed in, the powders and the additives might be formed into a mold or a cast and compressed, which sees us reach the green state, or the green form as it is known in the industry. Now in this form, we can see in the pictures attached here, the material still has a lot of defects, still has a lot of room for error, for weakness. But it also is a little bit more compact than the raw form. Now we take this green form or green state to be sintered or fired or heated into the final form by reaching specific temperatures, where you can see the crystalline structure form more compact monolith. Instead of a material with a lot of defects, we have very minimal defects in the final form. Now, more advanced processes to reach higher and better, more superior properties would see us use rheology, which is the study of flow of materials. Now, this is usually used for fluids, liquids, or gases. However, soft, or in quotation, soft solids, such as powders, can be studied through rheology, and that can help us study how the raw materials would be formed into the mold or cast or press, or however form of manufacturing we would use. That would also help us through the green state of, or the green form of the manufacturing process. Next is isostatic pressing. It is one of many modern techniques used for the manufacturing of ceramic materials. And in isostatic pressing, what happens is that the raw materials are put into flexible molds, and then those molds with the raw materials inside are submerged into a pressure tank full of water, where that tank would be pressed or pressured, and that leads to the pressure being divided equally along the whole mold, the flexible mold, which is why it is flexible. It gives more, it allows for the manufacturing of more complex shapes, possibly, and more uniform manufacturing. There's also the process of spray drying. Spray drying is used for the raw powders, which allows us to create more uniform and free-flowing powders, which are easier to deal with and creates a more uniform and compact final product. Possibly leads to it being stronger or just easier to work with, whatever the situation may be. Now, what are advanced ceramics? Well, advanced ceramics still adhere to the basic and traditional definitions of what a ceramic material is. However, they do exhibit far superior properties, thermally, physically, chemically, maybe. these superior properties are reached through more advanced processes or different material choices. As seen here in the picture attached there. This is an exhaust manifold for an internal combustion engine, and on the left it is corroded, on the right it is treated with a ceramic coating, which since it is very durable and very wear resistant, it does not corrode as easily, or possibly nearly does not corrode at all. It also is a great thermal insulator to keep the temperatures under the or inside the engine compartment of the automobile very low, or much lower than it would be without the ceramic coating. Now, the first highlighted application, more in detail than the exhaust manifold, I'll be talking about is the ceramic braking systems in cars. Now, these carbon ceramic braking systems have been in development since the 1970s, but that was for aircrafts. However, the first automobile which has used carbon ceramic brakes was in 2001 with the Porsche 911 GT2, as shown in the picture here. Now, why would anyone choose to use a carbon ceramic braking system in a car? Well, it is very durable. The carbon silicon carbide material used for these braking systems has a very strong crystalline structure, pretty similar to that out of diamond, not as strong as diamond, but fairly strong and much stronger than traditional systems using steel. The silicon carbide is also very heat resistant. And heat resistance in braking systems would greatly reduce the dangerous effects of brake fade. And brake fade basically is when braking systems lose performance, possibly stop working suddenly due to possibly the braking fluid boiling, or whatever it may be, due to extreme heat during excessive and repeated wear. Repetitive use usually happens on a racing track, in sports cars and in race cars. Repetitive and aggressive use of the brakes would raise the temperatures really high, up to a point where the braking system might fail. And so carbon ceramic brakes greatly reduce those dangerous effects due to their great heat resistance. They're also lightweight. They're also lightweight, and they can be up to 70% lighter than traditional designs using steel. And that greatly reduces the unsprung weight of a car, which makes it perform far better on a racetrack, possibly. Now, I do say racetrack, I have emphasized that, and it is one negative part of carbon ceramic brakes, is that they're very expensive and not needed unless required for repetitive and aggressive use, as seen in a racetrack or a sports car. That is why in regular passenger cars, everyday cars you see on the street, they would not have carbon ceramic brakes, as they are far more expensive than traditional steel brakes. And here is the crystal structure I've talked about. Here is silicon carbide on the left with this crystal structure above it. Next to it on the right is diamond crystal structure. It is not as strong as diamond, but fairly strong and much stronger than that of steel. The next highlighted application, also in the automotive industry, is catalytic converters. Catalytic converters are used for emissions control, to control the byproducts, the harmful byproducts of internal combustion. And here in this case, a ceramic monolith is used as the base for the metal catalysts used in the chemical reaction. These ceramic monoliths are used for their heat resistance and chemical stability through all those chemical reactions. Also with their thermal resistance and heat resistance. These catalytic converters can reach operating temperatures up to 8,000 degrees Celsius. And so a material which would take heat very well, it is very desired, which is why a ceramic monolith would be used in this case. Now, to the slightly more exciting part of the presentation, in the near future. And I say the near future since these are fairly new research papers talking about the future of this field. The first one is discussing coatings modified with aluminum oxide, and these coatings would be used as thermal barriers for advanced gas turbine engines. And this research has shown that the ceramic coatings modified with aluminum oxide perform thermally far better than traditional designs in uses for gas turbine engines. And that could possibly be put to use very soon in the very near future. And the next one is high entropy ceramics, where the researchers here employed artificial intelligence and machine learning to possibly predict formations of high entropy ceramics. This is a great breakthrough using artificial intelligence. It's very exciting. And but one thing is, while I was researching this, I did not possibly know exactly what are high entropy materials. And so I did a little bit of quick research, and I found that it is a new term. It is a fairly new term, which is why I haven't heard of it until recently. It is a fairly new term coined for materials or alloys using multiple different materials in high concentrations instead of having one main element with additives added on top of it. High entropy materials or alloys would have multiple elements in high concentrations. And so since we were talking about artificial intelligence and machine learning, it makes the future look uncertain since it is all just predictions of artificial intelligence. However, the present sure does look exciting, as well as the near future. Thank you for listening. That was the end of my presentation. Again, my name was Nassar Awaude, a mechanical engineering student from Palestine. And thank you for listening.
Thank you very much, Nassar. Now back to you, Raymond, with your question.
I was going to say Farah first, ladies first, if you wish to.
That was really interesting, very exciting, and as you said, lots of different challenges coming up to the future. And I guess I wanted to explore that because one of the things you did mention is the cost of using these new materials, quite expensive. So where do you actually see it going into the field of engineering, and what kind of challenges do you see with that?
Well, the current use, since they are very expensive, it is only used when those braking systems give a competitive advantage in motorsports or in high-cost luxury cars. I did not see any development which would lead to those technologies trickling down into regular passenger cars, so I do not know how to predict this future.
Okay, thank you.
No problem.
Daniel?
Yes. I'd actually like to ask a question again on the cost. I mean, why are ceramic components expensive?
Well, not all, but this specific application with silicon carbide is expensive since the machining of it and having to create a carbon fiber weave, and then with the resin and turning it into silicon carbide. And as we know, silicon is pretty expensive. And again, the machining of it and turning it into a braking system would lead to it being fairly expensive.
So the production process.
It's mainly the production process and silicon.
Okay. One question actually you mentioned in your presentation and in your answer to that question about the machining of ceramics. My limited understanding is that they are extremely hard. How do you machine them?
Well, these braking systems start off their production process with a carbon fiber weave, and then the silicon or the ceramic part is introduced. So they are formed first as a carbon fiber weave and then turned into silicon carbide.
But earlier on in your presentation, you said that the ceramic is formed and sintered and then maybe further machined.
Oh, well, yeah, the final machining or final production would see maybe polishing or it's mainly just polishing up any errors made in the production, not really any in-depth machining.
Okay, thank you.
No problem.
Can I ask another question? Yeah, could you tell us something about the ecological impacts of these advanced ceramics? I mean, things like the energy required, or the whether they're carbon neutral, if production processes can be made carbon neutral or more ecological.
Well, I did very briefly look for this specific topic and how they can affect the environment. However, I did not see any negative or positive. In general, research hasn't been done on this. Maybe because it is commercialized, so all the research I've seen was from manufacturers themselves. So
not accessible, you mean?
Oh yeah. I did not see anything talking about the environmental effects of the production of these materials.
Have you looked at the use of ceramics other than in the automobile industry?
Well, they could be used in biomedical engineering, artificial teeth with orthodontists. However, I did choose this topic because of the automotive industry. However, yes, they are used in biomedical engineering mainly, computer engineering as well.
Yeah, and I was thinking maybe aerospace as well.
Oh yes, that's also a very exciting field.
So has your research brought to you any ideas of any? Have you got some innovative ideas that you've had, or things you think you'd like to develop yourself in this area during the next few years?
I think we could possibly use it inside the home, maybe for surfaces. So instead of using those coatings we use for car paint or the thermal coatings in gas turbine engines, maybe we could trickle down those technologies to create for cooking surfaces, maybe, or possibly that's one thing I thought of quickly.
So you might, are you interested in a research project on this later on, perhaps?
I did discuss this with one of my instructors in my university of having this as a graduation project, yes.
Interesting.
Farah, you have any more questions for him?
No, not at all. My questions was around sustainability and environmental, so that's been already.
Sorry.
Okay.
That's okay.
That's what happens when the judges don't sit together. I think that's fairly clear, actually. You mentioned how long they've been in use. Do you see them becoming more widely used as time goes on, or?
Well, as coatings and thermal barriers, yes, the very near future seems very promising in this range, and can see more wide use of it. But as more integral parts of machines, I think we're still not there yet.
Okay.
During the production processes, are there any risky or safety hazards that you've found that need to be addressed?
Well, maybe with the heat treatment, but even more advanced materials use fairly traditional processes with more advanced techniques. And so these processes have been perfected throughout years and decades. So it is not very dangerous, only maybe with the heat treatment and the final polishing if done by hand.
Okay, thank you.
One question from me, perhaps. You mentioned the sintering takes place under use of heat, and you did mention in some cases isostatic pressure. Is the sintering always under pressure, or is it sometimes just heat?
Oh, the isostatic pressing happens before the sintering process, where the material is molded and then sintered. So the molding takes place in isostatic chamber.
Okay, but the sintering itself is just temperature, no heat, no pressure.
Yes.
Okay, thanks. I just didn't know that. I wanted to know. Thank you.
No problem.
Farah?
No, I'm okay.
Daniel?
I think we've covered the questions. Thank you.
Well, thank you very much indeed, Nassar.
It was my pleasure.
Thanks very much.
Thank you, Nassar.
Thank you.
Thank you very much to you all. Now we will take a 10-minute break. So we will be back a little bit before 4:10 with our next contestant, Nicholas. So if you want to have a coffee, now it's your time to go and make a cup of tea. And I will see you before 4:10. See you in a bit.
Okay, thank you.
We are engineers, and for every true engineer, our profession is all about constant change and continual improvement. It's about innovation, about finding ways to make the world work better. And right now, engineering is evolving faster than ever. Outward looking and open to new ideas, it has never been more exciting and daring.
I think machine learning and artificial intelligence will take huge steps forward.
Simulation is going to play a more important role.
Without a doubt, it will be increased computing power.
AI is the electricity of the future.
Quantum computers.
Low carbon technologies. Cutting down on fossil fuels, making the way we make energy a lot more greener.
Getting energy in a sustainable and environmentally friendly manner.
I think it's the potential to make a real difference in the world, both in terms of the environment and the economy.
Boosting the efficiency of how we use energy.
And in this dynamic environment, the way we learn, the way we live and work has changed. Information is instant and everywhere. Knowledge has broken down boundaries. Engineering disciplines are converging. Yet engineering careers are diversifying. Everyone and everything is multidisciplinary. The silos and boxes have gone. Artificial intelligence is reframing what is possible. And being an authority is no longer simple or easy. The emerging generation of engineers demand relevance, 24/7, 365 days a year. And now that any innovation can turn markets, lives and societies on their heads, they want the opportunity to take responsibility. So what will the institution of the future look like? How will it need to evolve to keep future generations engaged and inspired?
I'd like to be part of a community of engineers that embraces the exchange of ideas. I don't like being siloed.
By working all together, we can see the bigger picture.
I like to belong to a community where there's plenty of professionals coming from complete outside engineering.
We need to share across disciplines.
I think cross knowledge become way more important. We cannot just become purely mechanical engineers. We have to have also knowledge from, for example, electrical engineering.
But also, during this crossover communication, innovation is often spurred.
Engineers in the future will need programming skills and software skills to better integrate the mechanical system with the software to promote automation.
I'd also like to be able to take any problem to them at any point and receive guidance and encouragement.
Coming together and really solving problems together as one.
As modern engineers, this new reality presents challenges. But most importantly, it presents opportunities. Opportunities to innovate, to invent, to inspire, to create a truly global engineering community of engineers as they work to develop throughout their careers, of employers as they seek to attract and retain the brightest talent, of academics as they look to produce the type of engineers the world needs. The institution of the future will be the one that truly embraces this change, so that it not only survives, but thrives.
My name is Jade Abbott, and I work as the Global Account Manager at the Institution of Mechanical Engineers. Professional registration is an international recognition of your competence and ability as an engineer. It is a globally recognized benchmark that your employer can look at and know that you're deemed competent by an external governing body. So in this case, it's the Engineering Council of the UK. Professional registration is valuable for developing engineers because it opens up a lot of new career opportunity for you. It can unlock earning potential as well. A lot of employers value it very highly in terms of when they're looking to work with new clients, when they're looking to employ someone, when they hope to promote someone. Becoming registered allows you to achieve your professional ambitions and gives you that chance to reflect back on what you've been doing, especially as you're moving through your career. To achieve professional registration, you need to meet certain standards set by the Engineering Council as laid out in the UK spec or the UK standard for professional engineering competence. There are two ways to meet these standards. One part is an academic standard and the other is an experience or competence standard. You become professionally registered through your professional engineering institution. The program is useful for developing engineers because it allows you to track and monitor where you're sitting in your competence development, especially at the beginning stages of your career. It'll allow you to remain motivated, but it also is a great way for you to monitor where you might need further development or support, even from a career standpoint. It makes sense to begin using the program now to make the most of your associate membership.
I'm Ken Seger. I've worked at Johnson Matthey Catalyst in Royston for the past 10.5 years. I chose to become professionally registered in order to fulfill almost a childhood ambition. Sounds a bit unusual, but I'd been to some Institution of Mechanical Engineers sponsored lectures as a young lad when I was only 12 years old, and at around that time I became aware of the letters IMechE behind one's name and how that would represent being a member of this institution and a recognition
Can everybody still see? Hello? Still working?
Hello, Adam.
Okay. Just checking.
We're still here.
Yeah, it says we're back. I don't hear much.
I guess we're back a little earlier than the videos must have lasted less than 10 minutes, huh?
Well, the one seemed to run out of sound partway through or something.
There we go.
Yeah.
Okay. It sometimes cuts out the sound. I do select every time include computer sound, but sometimes it cuts it out.
Yeah.
I don't know why. Maybe network issues or something.
It was funny because
I'll
it was
try.
running and then it suddenly stopped the sound and actually stopped the picture as well.
Yeah, I have no explanation.
None demanded.
So we start in a couple of minutes.
Okay.
Is Nicholas here with us?
Hi, hi, can you hear me, everyone?
Yeah,
That's
okay,
good.
Great.
Yes.
Yes.
Is Guillermo?
Yes.
Okay.
Yes. I'm online.
Okay, great.
I think Nicholas just left us.
Yes, he probably pressed the wrong button.
Yes, he's back.
Hi. Sorry, I'm not sure. I'm not sure what happened.
We all do it sometime or other with these meetings. Yes, even though in one of the presentations, the first presentation, there was a period in which sound wasn't perfect. It wasn't too bad. I mean, I think we still heard practically everything and could follow it all. So
Yeah.
don't be discouraged.
Okay, so it's 10 past 4, and since both of our contestants are here, we will move on to our next contestant, Nicholas Sammut from Malta. Hello, Nicholas.
Hi everyone.
You have 1 minute.
Okay. Thanks everyone, first of all, for having me here. My name is Nicholas Sammut. I'm Maltese. Malta, in case not everyone knows, it's a small country off the coast of Italy. I don't blame you if you don't know where it is. It's a very tiny island. I'm graduated in mechanical engineering, and throughout the 4 years I was at university, I took part in Formula Student throughout the 4 years. And in fact, my engineering presentation here is focused around a project I did within the team. Basically the design of a shroud or cowling system between the extraction fan and the radiator to improve the heat transfer and the flow of air through the actual radiator. So I have 15 seconds left, but I think that's pretty much it. And obviously you'll all hear the detail in the presentation. So thank you very much.
Thank you, Nicholas. Nicholas Sammut, an optimization analysis of a cooling design between water-to-air heat exchanger and extraction fan, an optimization analysis of a cooling design between water-to-air heat exchanger and extraction fan, Nicholas Sammut.
Good afternoon, everyone, and welcome to my presentation. My name is Nicholas Sammut
from Malta, and I'd like to start off by firstly thanking you all for being here and for giving me the opportunity to present to you my engineering project, which also happened to be my final year dissertation. My project was carried out as part of a much bigger picture, and that would be Formula SAE, Europe's most established educational motorsport competition, where top universities from all over the world are challenged to design, fabricate, and compete with a Formula-style race car. Events are split depending on whether they are dynamic or static. The dynamic events test the car's driving ability through the acceleration, autocross or sprint event, a test of handling called skid pad, and finally the endurance event, which is arguably the most challenging and requires the car to drive for around 22 kilometers. On the other hand, static events consist of presentations and they test the teams in all aspects, including the design of the entire car from an engineering perspective, the ability to budget and account for every part financially in the cost presentation, and finally, actually pitching the car as a product using a complete and holistic business plan. University of Motor Racing is our own Maltese Formula student team. It is made up of over 30 highly dedicated students whose main aim is to represent our country in Formula student competitions abroad. In fact, our last major competition took place in Silverstone of summer 2018, where we finished 28th place out of 82 teams. It was our best result yet. And our aim as a team is to always create and maintain the necessary framework to continuously improve our cars. But while the team has focused on many areas of the car so far, the idea of an optimized cooling system had not yet been addressed in the team. So some cooling fundamentals first. The main component of a car's cooling system is the radiator. A radiator is essentially a heat exchanger which receives hot coolant from the inlet, and the hot fluid passes down through the core tubes and cools significantly before it reaches the outlet. Of course, higher airflow through the radiator typically means better cooling rates, and in fact, most radiators incorporate a cooling fan, which is either mounted in front or behind the radiator. This is a continuous process and is an essential part of the car's operation. But perhaps the most interesting feature on the radiator are the fins which surround the radiator core. They do serve a very specific purpose, however, and that is to increase the rate of heat transfer by increasing the surface area of the heat exchanger core. These fins are also what happen to make radiators such as this one rather challenging to simulate in computer software. Formula student race cars are designed around a set of very rigid rules. While they are engineered to have high performance in terms of acceleration and handling, they're also designed to operate at relatively low speeds, rarely exceeding 100 kilometers an hour. This is because races typically take place around a very confined track consisting of tight corners, and it is those racing conditions which often push engines to their limits and put a large strain on the vehicle's cooling system. And this ultimately results in water temperatures, hot fluid temperatures, which exceed the engine's maximum operating range. And so this problem was addressed by first determining the most suitable approach to modeling the heat exchanger. Now, several different approaches can be taken to improve the heat transfer to a radiator, but the main objective of this project was to design and simulate a shroud system to increase the total mass flow rate of air through the radiator, thereby improving the overall rate of convective heat transfer. This presentation will take you through the entire design process of the shroud, from the first principles and simulation up to the manufacture, and finally the experimental validation of the part. According to literature, conventional modeling of the heat exchanger would require an excessively large number of elements due to the complex geometry of the radiator fins. An alternative approach, however, is to model the heat exchanger as a porous medium. And to do this successfully, ANSYS Fluent, the software used for this dissertation, requires the user to define two important parameters: Firstly, the inertial resistance coefficient, and secondly, the viscous resistance coefficient. And for a heat exchanger, the most suitable approach to determine these coefficients is through its pressure drop data, which would typically be in the form of a relationship between the incident airspeed and the corresponding pressure drop across the heat exchanger core. However, the team made use of a custom-made radiator, and of course, with no data sheets available, these force coefficients had to be obtained experimentally in the faculty's wind tunnel lab. The figures here illustrate the experimental setup used for the experiment. The radiator's cross-section was mounted inside of the wind tunnel, and a hot wire anemometer was placed in front of the radiator and was used to measure the inflow speed. Also, a pitot static tube was placed both in front and behind the radiator to measure the static pressure drop across. And on top of this, additional static pressure ports were created on the walls of the wind tunnel as a reference to increase the level of reliability in the experiment. The graph in this slide plots the relationship between the inflow speed read by the anemometer and the pressure drop on the corresponding y-axis. Then, by relating the equation of the graphs to the momentum equation for porous media, both coefficients could be obtained. In this case, 3 sets of coefficients were derived, again because there were 3 sets of static pressure ports in place, and an average of these 3 sets of coefficients as with the final coefficients used later on in the computer simulation. The next stage of the project involved computational fluid dynamics software. CFD was first tackled by modeling the current cooling setup at the time, which had the extraction fan directly stuck onto the back of the radiator core. Now, this setup was first meshed in ANSYS Workbench, where a fine hexahedral mesh was used for the radiator itself, and with a sphere of influence surrounding the zone which was deemed to be the most crucial for us. Using a sphere of influence to mesh this localized zone was actually very helpful in this case because it allowed for the creation of a much finer mesh to better capture fluid behavior around the radiator. And the accuracy of the mesh was validated through a grid-independent study, but also a domain-independent study was carried out to ensure that the size of the fluid domain used was sufficient to capture the entire behavior of the flow. The first step in creating the fluid simulation was setting up the correct boundary conditions and viscous model. Through the literature study, it was determined that the K-epsilon realizable model was in fact the most suitable for this application. It is in fact often presented as the default model setting in many commercial software packages, and after importing this model into ANSYS Fluent, the radiator could then be defined as the porous zone. And in fact, it was at this point where the coefficients obtained previously could be input for the relevant direction vector of the flow. The fan itself was declared as an internal fan zone, and this was modeled as a specified pressure jump. This was done by first obtaining the pressure drop data sheets provided by the fan manufacturer, and this could be then converted to a relationship between the velocity and pressure drop, really much like the approach taken to the radiator itself, in fact. Like this, the fan's behavior could be defined in terms of a polynomial profile, and using the standard equation for time-dependent functions, it could then be modeled into Fluent. Post-processing was done on simulations both with and without the fan. This was done to compare both models and to ensure that the fan was operating as expected in the model. In all simulations to follow, the velocity and static pressure were the variables of interest. And when observing these contours, the effect of the fan on the flow through the radiator is visibly significant. And this was enough to confirm that the fan model was indeed working correctly. The velocity contours were plotted and illustrated on the slide, and where the plots show an incident velocity of 10 meters per second in the pre-stream, and then a wake of turbulent air forming behind the radiator. Now, a phenomenon which is quite notable is when the fan is activated, and that the area of the radiator, which does not fall under the fan's catchment area, so to speak, will not be affected by the fan suction. And furthermore, with the diameter of the fan actually being larger than the radiator's width, there were parts of the fan extending beyond the radiator, and these parts were essentially being wasted. So it was deemed that with the introduction of a shroud, not only will it be shaped to accelerate the flow better through the radiator, but it will also be designed to capture the entire area of the flow. Once the original radiator configuration was correctly set up, the next step was to design the shroud and analyze its effects on the airflow. These figures illustrate one of the runs at 4 meters per second, where one can see how without the shroud, the pressure drop is again localized around the fan area only, while with the shroud mounted, the entire portion of the radiator is affected by the pressure drop. And these effects can be most visibly seen in the graph alongside the contours, which plots the air inflow speed and against the mass flow rate. And this was plotted for both configurations. The mass flow rate was obtained using Fluent by finding the surface integral for mass flow rate at the radiator interface. And as expected, the mass flow rate with the cowling is significantly more than without. However, as you can see, this effect is most notable at lower speeds, and beyond a certain speed, not only do the mass flow rates level out, but at higher speeds, actually the shroud begins to act as a blockage and does have a negative effect on the mass flow rate. But having said this, it is at these speeds that therefore is most critical. Over here we have a graph which shows the speed of one of our race cars in a typical endurance event, lasting again for 22 kilometers. Many times the speed of the car is seen to dip well below 10 meters per second. This was probably when turning a tight corner, for example. But this is when it becomes important. On top of this, midway through the endurance race, there is a required driver's change, where the car ignition must be turned off as the driver's transition, but the fan can be left on. And at this stage, engine overheating is a very common occurrence in competition during this time because of the lack of airflow, and so the introduction of a shroud can produce, as we can see here, mass flow rates when idle, which is comparable to when the car is traveling at 6 meters per second without a shroud configuration. With the potential effects of the shroud clearly visible, the next step was to analyze on different geometries, on the mass flow rates with the shroud. Surprisingly, 5 different cowling designs produced extremely similar mass flow rates, but what was different, however, was the way that the flow was distributed for each shroud design. In fact, distribution of flow for the initial design, as you can see here, the first visual, it is not that even. In fact, the largest pressure drop is concentrated on a localized area towards the bottom portion of the radiator, and then by shortening the shroud geometry and by introducing a more convex shape, flow distribution was actually being improved. The drag over the cowlings was also examined and was found to have negligible effects on performance, really. So in the end, the short convex shroud was chosen for manufacture, firstly being the lightest design, but most importantly, after showing the most ideal flow simulation, flow distribution. It was then decided that the material used for manufacture would in fact be carbon fiber because of its lightweight nature and its high temperature resistance. In addition to this, the team has been fairly experienced in carbon fiber manufacture and has had the resources available to carry out a task such as this. The mold itself was 3D printed due to the complex convex geometry, and this was followed by a carbon fiber wet layup under vacuum. And not only is the wet layup technique the simplest and cheapest method of composite manufacture, but it allowed for the part to be cured at room temperature and hence posed no risk of melting the mold, which was based from. And this is the final result. The entire configuration of the shroud, radiator, and cooling fan. Now, a critical part of any computational simulation is the establishment of a reasonable amount of confidence in the results obtained. And so validation of the CFD simulations project was done in two parts. The first part consisted of a non-invasive experiment, which was focused on finding an area-weighted average of the velocity of inflow through the radiator, and then a hot wire anemometer was used to record the inflow air velocity at several marked points on the radiator face, as you can see in the picture here. An identical simulation was then set up in ANSYS and compared to experimental results. The second part involved a single static pressure tapping on a suitable location on the shroud, which allowed for a direct comparison to the pressure found at the same location in the simulation. A discrepancy of 17.7% was found in the first experiment, and similarly 17% was found in the second one. And this level of discrepancy was deemed to be sufficient, especially since the fan was being simply modeled as a pressure jump, of course ignoring the effects of swirl and the effects of the fan blades. So it was there concluded that there was enough confidence in the study for it to be replicated and developed on in future simulations by the team. So the successful modeling of the radiator's air domain in reality was just the first step to obtaining a complete heat transfer simulation of the heat exchanger. Together with a working model of the radiator's water domain, the ultimate objective is to be able to accurately size the radiator via simulation. Similarly, as well as the radiator, a separate study can be focused on obtaining an accurate model of the fan itself, perhaps by using the moving reference frame approach. Optimization of the fan itself could bring a lot of potential benefits to the race car, namely significant mass reduction and energy savings, on the power budget of the car. I would say that overall, the most rewarding part of this project was being able to contribute to the team after being in it for my whole university career. And it was great being able to widen its knowledge in computational fluid dynamics, especially, and this giving it the ability to have a more competitive edge in its future formula student endeavors. So that was my presentation. I hope you enjoyed it, and I'd be more than willing to answer any of your questions.
Thank you very much, Nicholas. Back to you, Raymond.
Daniel, would you like to go first?
Yes, here I am, once I'm connected. Thank you very much. It's a very interesting presentation.
Thank you. Thanks a lot.
Yes, I was wondering, so your experiments were on a specific car, specific type of circuit. Did you discover any general rules for how you would be able to design shrouds or solve the problem in other situations?
So other situations, I think you mean beyond formula students?
Yes, commercial applications or something that more.
Okay.
Yeah.
Okay, so yeah, actually, so the problem which we first realized was that our engine was overheating a lot, especially during testing. And after, of course, doing research and discussing with, past team members and even sometimes other teams, many of them designed sort of a shroud cowling system to improve the airflow, especially when the car is traveling at lower speeds. And in fact, it's used very often nowadays in automobiles and normal cars. Of course, when you're waiting in traffic or waiting at a red light, you need to have a good amount of airflow through the radiator, and that becomes 100% reliant on the fan. And of course, having that shroud can really optimize the airflow through. So I think from a car application, especially in motorsports, what I did was I laid out the foundations for the team to be able to use it for future simulations. And the idea from there is to have someone to further develop it, combine that with then a simulation of the water part of the radiator. So basically my project was focused on the air domain of the radiator, so the actual airflow. But then this you'd have to combine it with the water domain, which is then the actual domain of water found inside the radiator. And then when you combine those together, you'll be able to obtain a complete model. Always, especially in racing conditions, the idea is to have your car as light as possible. So the end goal for all of this is to design a radiator which is as small as possible, so that your car can ultimately be faster. So in terms of competition, the reasoning behind all these FVAs, CFD studies, it's always mass reduction. So let's push the car to the limits, as light as it can be, basically. I hope that sort of answered the question.
Yes, thank you.
Thanks.
Okay, one from me, just a simple one actually.
Okay.
Did you actually complete the endurance phase?
Yes, we did. Actually, it was the first time we had ever completed it. It was in 2018, which we completed in Silverstone. And in that particular year, I was actually the team leader of the team, and it was our biggest goal of that season to be the team that actually completes the endurance, because we've been sort of always unlucky, so to speak, up till then. But you know, after a hard year of working late and always being in the garage and perfecting things, we finally managed to complete, and we were really happy. We really ended that year on a good note.
That was good.
Thank you.
I'll go ahead, Raymond.
Yes, please, Farah.
Okay. Thanks, Nicholas. Really fascinating.
Thank you. Thanks a lot.
The fascinating thing with Formula Student, it's not just about technical challenges.
Yes.
It's a whole bunch of different skills and challenges. And I was wondering, other than the technical challenges, what were some of the other challenges you faced, and what was your approach to overcome these?
So yes, that's a really good question, actually, because in 4 years of me being a Formula Student, having many different roles in the team, I can confirm that challenges are more than just the actual building of a car. It goes quite beyond that, especially when I was in more of a team leader, having a more team leader role in the team. It was like half building a car, then half political related issues, communication with university, maintaining relationships with sponsors who ultimately funded our entire car, because at the back of your mind, you have all your designs nice and perfected on software, but you need to get the money from somewhere. So especially being in engineering itself, the course, it went well. It always goes well with Formula Student, because it teaches you a lot of soft skills, not only with your peers in the team, management, team related, internal challenges you might face within actual people of the team, but externally maintaining contacts with sponsors, the people in the competition, of course. So that's definitely a big part of, apart from just building a car. But then in the competition itself, specifically, you have to arrive there and you have all your presentations, which have to be perfected and ready and rehearsed. You have to have your, it has to be very pre-planned when you're a team at a Formula Student track, because you have the competitions, you have certain times that you have to be there for the event. If you're late to one, you might actually miss it completely. So apart from having your car in perfect condition, you have to have all the logistics and competition related things sorted. And I'd also want to mention a funny story, but when we competed in Italy in 2017, we actually got really bad food poisoning on the campsite, and we ended up 28 members out of 35 people in hospital. So, and we missed 2 events, at least it was just 2, but that goes to show that around the actual building and competing with the car, there are lots of other problems which can occur, some you might not even have thought about before. So,
thank you.
Welcome.
How many of these skills have you been using since Formula Student as you start your career?
I would say that actually being a Formula Student was extremely important for where I am right now, because my current job, I've been graduated for just over a year now. it's a sort of consultancy-based job where we do a lot of process engineering and a lot of management. So it's very people-based. It's a very people-based job, and of course, this would have not been possible. But I learned a lot of management skills in the team, and I learned how to deal with many different kinds of people and different kinds of work ethics also in the team. So now when I come to work for example, we're at different clients almost every day, I find it much easier to establish relationships with people. I can maybe read people easier, and ultimately, it is again problem solving, and of course those were definitely skills which helped me a lot in that while being in the team.
Thank you. Daniel?
Yes. So you mentioned that the overall goal is to reduce weight, reduce size of the items. So this probably brings in lighter items which possibly are subject to more vibrations, perhaps risks of detachments. So my question is, how did you handle the unknowns, like the safety aspects and the reliability aspects of working with lighter and less robust materials and parts?
First of all, when we are unsure or we don't have the resources available to do a stress analysis or any form of analysis on a part, we do take quite a big safety factor into account. We'd rather, go in a bit heavier, but a bit over-engineered. That's kind of what we've always done to make sure that, we don't have any last-minute surprises. But in terms of, certain issues which might face with making parts as light as possible, we've been focusing a lot on our wheel assembly, especially our uprights. We're always reducing the weights of those, and we do make sure that we test as much as we can on the track, provided thanks to our university, before going up to competition. In fact, when we did complete our endurance at Silverstone, it was also not a coincidence. The first time we had done multiple endurance tests on the track before we actually went up. I can confirm that whenever you go up for a Formula Student competition without testing, you're always gonna have a major problem happen. And this is whether you are gonna have parts which are really light or whether you have everything over-engineered and as safe as you think it is. There's always gonna be something that's gonna crop up, so it's best to catch as many of these problems by testing months before going up to compete if possible. So,
thank you.
Welcome.
Farah, anything else from you?
No, nothing else from me, thank you.
Oh, did you enjoy the Formula Student as a competition? Did you find it a worthwhile experience?
It was really one of the best experiences of my university career. I'm so glad that I joined as soon as I joined university. Going up there, meeting all those new different teams and all other teams with people who are just as ambitious as you are and who have different ideas, and of course bounce off different sort of ideas and developments for future cars. That was great. But more than that, it was just a pleasure in a way to see the level of professionalism and competitiveness in an event such as this. And me personally, I'm quite into sports and everything, and this was very much like you're an athlete and going to race at a competition. It's a great competitive experience, maybe not physically, but academically and
thank you,
of course engineering related. But thanks for the questions.
Thank you.
Thanks very much.
Thank you very much. Time is up for questions and answers. And now we move to contestant. Let's welcome Guillermo Muñoz. Guillermo, are you there?
Good afternoon to everyone. Good afternoon.
You have 1 minute.
Okay. Good afternoon to everyone. My name is Guillermo Muñoz. I'm from Sevilla, from Spain. I am a student from the University of Sevilla. I am I'm studying the Master of Industrial Engineering in the specialty of mechanical. I belong to IMechE Iberia. In my presentation, I'm going to speak about exoskeletons. I'm going to speak about the influence of exoskeletons in our life. How can they improve our quality of life? How can they help people to live better? My objective, my goal is to promote the knowledge of exoskeletons in population, so as people can know what they can do, how they work, and how they can be a help in our society, so as we can live better. I hope you to enjoy my presentation.
Thank you very much, Guillermo. Guillermo Muñoz, Exoskeletons, a way to improve our life. Exoskeletons, a way to improve our life. Guillermo Muñoz.
Good afternoon to everyone. My name is Guillermo Muñoz. I am from Seville, Spain, and I would like to introduce you my presentation, which is Exoskeletons, a way to improve our lives. Without further details, I'm going to introduce you the points of my presentation. I'm going to start speaking about why I'm talking about exoskeletons. Okay, my motivation to speak about this. In the second point, I'm going to define what is a mechanical exoskeleton. I'm going to give you a definition, a brief definition. In the third point, I'm going to explain you the main types of exoskeletons, passive and active. I'm going to tell you in further detail after. In the point number 4, I'm going to speak about the uses of exoskeletons. There are 3 main uses I'm going to talk about. In the points number 5 and number 6, I'm going to tell you about experiments made in exoskeletons in the last few years. First in passive exoskeletons and second in active exoskeletons. In the 7th point, I'm going to tell you about the conclusions I've got from making this presentation. And the last point, I will be open to your questions. Okay. So let's start. As I said, speak why I'm talking about exoskeletons. Okay. I have 3 main reasons why I'm doing this presentation. In first place, in my opinion, exoskeletons are a really important tool to make the people's life better. Okay, exoskeletons can help people to walk, to recover the ability to make certain movements. So people who have suffered an injury, who have suffered an accident when they are young, so they can have an easier life wearing an exoskeleton. In second place, exoskeletons have experimented a great advance in the last few years. Exoskeletons are not new because they were invented like in the past century. But in the last few years, a lot of great advances in their development have been made. And in third place, last but not less important, I would like to promote you and the public in general the use of exoskeletons because, in my opinion, it's a very important tool so as to people can live better. Okay, so I think many people is not really aware of the uses of the exoskeletons, of the concept. So I would like to help people to understand better the exoskeletons. Let's define what is a mechanical exoskeleton. A mechanical exoskeleton is a device which contains some mechanical elements like lever, engines. These elements provide the system with an additional energy that help the person who is well need to perform some movements. Okay. I want to say that the exoskeleton is not a substitute of the human body in the act of performing the movement. The exoskeleton provides an additional help, but the movement, the person who is making the exoskeleton must start the movement. Okay, but the exoskeleton is an additional help. Okay. There are 2 types according to the form of energy. Okay, in first place, active exoskeletons are powered by an electrical engine that produces an assisting torque. Okay, these exoskeletons are more difficult to produce, are more expensive. Okay, they are more complicated, but they provide more torque because they have an electrical engine, so they are more useful. Okay. On the other hand, we have passive exoskeletons whose energy is produced by elastic elements like springs and dampers. This energy is stored, is released during the motion. Okay. According to their use, we can classify in 3 types of exoskeletons. In first place, medical exoskeleton designed to help victims of diseases and accidents to perform diverse motions. Okay. In second place, we can talk about industrial exoskeletons. These exoskeletons are are designed to help workers in the industry to perform certain movements or to stay in a position for a long time. Okay. In third place, I would like to talk about military exoskeletons. They are designed to help soldiers to perform difficult tasks, for example, crossing difficult terrains. Okay, these exoskeletons are designed to help soldiers, to help members of the armies. In this picture, we can see a soldier from the United States Army wearing a mechanical exoskeleton. Okay. Now I'm going to tell you about experiments made in passive exoskeletons. I remind you that a passive exoskeleton is an exoskeleton which it contains springs, dampers, which store the energy and release it during the motion. But they have not an electrical engine. They are not as powerful as the other exoskeletons, the active exoskeletons. Okay, I would like to start with the LAEVO exoskeleton. Okay, with experiments made with LAEVO. LAEVO is one of the most important what is the most representative exoskeleton that exists nowadays. It is connected to the body through the back, the chest, and the thighs. So it means that this exoskeleton is connected to the body. Is designed to help the people to move the upper limbs. Okay. I'm going to tell you about an experiment which was made 4 years ago by some scientists. They wanted to study the influence of this exoskeleton when workers were making some typical tasks in the industry. Okay, there were 2 tasks were studied. In the first task, the person had to simulate an assembly. Okay, they have to bend their back and taking a piece. Okay, they have to spin their back and assembly the pieces they have taken. Okay. In the second task was more simple. It was only to a static holding. They had to hold their back static with a certain degree of bending. Okay. The results of the experiments show that wearing the exoskeleton, the person had to make a less effort wearing the exoskeleton, so they were less tired wearing the exoskeleton. This is good because the exoskeleton. This is good because the exoskeleton is fulfilling the objective of producing the person more is helping the person who is wearing the exoskeleton to make the task easier. Okay. In the first graph, we can see the electrical activation of the muscle is less wearing the exoskeleton. Okay. In the first task and in the second task. In the third task, in the third graphic, we can study the discomfort was studied. Okay. in this graphic, it's important to speak about the discomfort because one of the objectives of the exoskeletons is not only to help the people to perform move, but also to be the less discomfortable possible. I have to remind that an exoskeleton is a heavy device. Okay, it can weigh like 6 or 7 kilos. So it's a heavy device you are wearing. So it could be uncomfortable to wear it. So it's important to designing an exoskeleton to make it the most comfortable possible. So in this experiment, we can see that in the legs, the exoskeleton was annoying the person more than without the exoskeleton because the discomfort is bigger. Okay. Now I'm going to tell you about the next exoskeleton, exoskeleton. Okay, this is another exoskeleton also designed to perform tasks involving upper limbs as the previous exoskeleton. It can also be useful for industrial workers. So in this experiment, this experiment is very similar to the previous one. This experiment, workers were asked to perform 3 tasks typical in the industry. Okay. Here we have the 3 tasks. In the first tasks, we have the woman lifting a load and lowering it to a more little height. Okay. In the second task, we can see an individual working with a load, carrying a load, and working with it. And in the third task, we can see another individual unstacking a box in the left side and spinning their body and stacking it in the right side. Okay. The results in this experiment show that the muscle activity is bigger wearing the exoskeleton in some muscles. For example, in this muscle is tibialis anterior, and this muscle is the triceps brachial. Okay, the activity wearing the exoskeleton in the black color is bigger. So the exoskeleton is not fulfilling the function to make easier the movement to the person who is wearing it. Okay. So this exoskeleton is not fulfilling the function in the lift task. In the other task, it happens the same. In the stack task, it happens the same, that the muscle activity is bigger in those muscles, in the tibialis anterior, in the triceps brachial. Only in the walking task, the activity is the muscle activity is smaller wearing the exoskeleton. Okay, it's in the only task the exoskeleton fulfills their function. In this central graphic, we can see the deviation angles of the in the 3 tasks, in the lift, in walk, and stack, and we can see in some muscles, in some joints. Okay, in some joints the deviation angle is bigger wearing the exoskeleton, which is a bad news because the exoskeleton, no, it's a good news, sorry, because the exoskeleton allows to bend more the joint, but in some muscles it happens the contrary. So we can see that the exoskeleton is not as good as desirable. So it's not as good as the previous exoskeleton. Now, I'm going to talk about an experiment that a professor of the University of Sevilla, Professor García Vallejo, and me, we studied. We made an experiment with this active exoskeleton. This is the Scaffold Experiment. Okay, this is a Scaffold exoskeleton. This exoskeleton is active because it's an electrical motor which provides an additional torque to the person who is wearing this exoskeleton. Also, it has a clenched ankle. It's an artificial ankle which makes more easier the bending of the ankle. Okay. In this experiment we studied the influence of the device in a walking guide cycle performed by individuals. Okay, these individuals had suffered an injury, a spinal injury, They wore the exoskeleton, and we made modifications. We made changes in the parameters of the exoskeleton, studying the magnitude of these changes. Okay. As you can see, this exoskeleton is wearable only for legs. Is thought to the lower limbs. Okay. I'm going to show you the mathematical model of the person used to perform the experiment. Okay, it's a mathematical model centered in the lower limbs, because we use we only use for the seven bodies. We use the hat. The hat is the pelvis. Okay, we use the 2 thighs, 2 chunks, and the 2 feet. Okay, and 9 generalized coordinates. 3 for the trunk, okay, and 2 for these angles, the angles of the pelvis, 2 for the angles of the knees, and 2 for the angles of the in the feet, okay, in the ankles, okay. We change, so as I said, we change parameters in the orthosis, analyze the deviations, okay. Now I would like to show you the most remarkable results we obtained in this experiment. Firstly, in the first graph, we represent the vertical coordinate of the pelvis versus the normalized time. Okay, we got the time and divided it by the maximum time. Okay. In the green line, we can see the person wearing the original exoskeleton without changes. Okay, without change. In the red line, we can see the vertical coordinate of the person wearing the exoskeleton after an increasement of the moment of inertia of a 5%. Okay, we make the exoskeleton heavier, while the blue line represents the person wearing the exoskeleton with an increasement of the 10% of the moment of inertia. So we can see that wearing the exoskeleton, the movement gets more stable. Okay, the stability of the movement gets increased. Okay, so this is good. This means that the exoskeleton fulfills its objective of make more easier the movement performed by the person. Okay, in these 2 graphs, we can see a blue line. Here is black line, but it's the same. We can see represented the ankle orthosis torque here for the right ankle, and here for the left ankle. We can see the red line wearing the exoskeleton without changes, and the blue line wearing the exoskeleton with an increasement of a 10% of the moment of inertia. Okay. What does they mean? This graph means that increasing the moment of inertia of the exoskeleton, we can perceive that exert a bigger torque. The orthosis is the ankle orthosis we've seen before is exerting a bigger torque. So it is this is making more easier the movement of bending the ankle. Okay, so this means that this exoskeleton makes a good job, is making more easier the movement for the person wearing it. So I would like to finish with some conclusions. In the first place, we can see that exoskeleton may suppose an important improvement in our life quality, because we have seen that they allow us to perform some movements in difficult situations. We can see that some movements they are more easy to perform them wearing the exoskeleton. But also another conclusion I've taken from this is that further research must be done yet, because as we have said, some exoskeletons can be an obstacle for making the movement, because the discomfort could be bigger. Even the movement performed by the own body, human body, could be bigger wearing some exoskeletons, and this is not the objective of the exoskeleton. Okay, so now I open for your question. give you thank you. I say thank you for paying attention for my presentation. Thank you very much.
Thank you very much, Guillermo. Back to you, Raymond.
Okay. Farah, do you wish to ask something?
Yes, I can start. Really interesting, very futuristic.
Thank you very much.
I was wondering, what are some of the barriers holding back mechanical engineers and designers for creating a more functional and usable exoskeleton?
In first place, in my opinion, one of the strongest barriers is the money, because first to research, because researching requires money, requires investment to know how can we explore the exoskeleton, how can we change the exoskeleton, the engine it has, the comfortability. As I said in the presentation, comfortability is also very important because you are wearing a heavy exoskeleton, a heavy device that weighs like 7-8 kilos. So this the first barrier I would say is the investment. It's needed that governments make a strong investment in not only in science and engineering, but also in it's important that the companies, okay, the engineering companies make a focus on the investment of the researching of mechanical exoskeletons. Sorry. Another barrier it could be in this in this situation of the COVID. Also, I would say it is not easy to make experiments trying the exoskeletons. Okay, I mean it's difficult to find people who are to make experiments with a lot of people which are open to try the new exoskeletons, to study the effects that exoskeleton produce on them. Okay, it's difficult because it's a situation where you cannot make a group of people to try these experiments, so it's difficult. I would say these are now the two main barriers in the mechanical engineering to try the exoskeletons.
Thank you, Guillermo.
You're welcome.
So Daniel?
Yes, thanks. Yes, thank you. Yes, I know that passive exoskeletons are used in Fiat assembly plants, not far from where I live. But do you know the potential market size in other sectors, and what is the current penetration of the market?
You mean in other sectors than
other sectors? Yes, yes.
For example, in other sectors, you mean in the industry? So you mean in
any industry? Do you know what the possible market size is, and what success do these companies have in how many have actually been sold, or is the market still completely open?
I think about the integration of people who has a limitation of their movements in the industry. For example, people who has suffered an accident, for example, and has lost partial mobility, for example, not only they can walk again and perform certain movements, but they also can penetrate in the industry, okay? And they can do certain jobs that they couldn't do without the exoskeleton, even in the industry, for example. They could, for example, a person with exoskeleton could play a role, for example, in a factory, for example, wearing the exoskeleton. This person could fulfill some roles that couldn't, for example, carrying a bag, carrying a load, transporting some sort of mechanical, for example, artifact. I don't know. This is the first thing I will think of: the integration of people who have suffered a loss of mobility in the industry is the main advantage I will see.
Okay, thank you.
Thank you.
Okay, one question. Have you done tests using disabled people with these to see how they got on with them?
Yeah, in the active, the experiment with the active exoskeleton I've shown in the presentation, we worked with people who have suffered an a spinal cord injury. Okay, they have suffered a limitation in their movement. So we studied how the exoskeleton, we changed its parameters of the exoskeleton. For example, we changed the moment of inertia, as I said, but we also changed, for example, the maximum power of the engine of the exoskeleton, and we studied the influence, how it changed the motion of the person. Okay, we studied a walking gait cycle, and we saw that the changes in the exoskeleton improve the performance of the person of these disabled people, which were performing this walking cycle, gait cycle.
Okay, what sort of time did you test that over? I mean, it's one thing to wear something like that for 10 minutes. It's another to wear it for a couple of hours.
Sorry, could you repeat your question, please?
Yeah, when you tested it with these people, what sort of time was involved for them to wear it? Because obviously wearing a relatively heavy thing for a short time is quite easy. For a longer time could not be so easy.
No, the part of researching the time, the investigation with the people, the wearing the exoskeleton was made by the professor. Okay, I was required. I was asked to do the part of study the influence. Okay, to see I wasn't myself present at the investigation with the people. It was the professor. Professor from the University of Sevilla, but I studied the time was 1 year, 1 year of study. I think it was 1 year. The time was people was selected and making the investigation to collect the data, okay, and the influence of the exoskeleton and the changes, okay. I think this answers your question.
No, I meant more, how long was the actual individual session?
Individual section. I remember that it was like you mean to do the cycle of
how long did they wear the thing for at one time?
Okay.
10 minutes or 10 hours or?
No, 10-15 minutes to do the cycle. Okay, to do the cycle. Sorry, I didn't understand before the question. Okay.
That's okay.
Okay, thank you for your question.
Daniel, you have something else to ask?
Yes. I'm thinking of with the active exoskeletons.
Yes.
Particularly with people who are disabled, who might not have senses or have diminished senses. How do you protect the safety of the people from the powered motor making movements that can actually hurt the person instead of helping them? And does it create a safety and legal responsibility?
Yeah.
How do you mitigate that?
You mean the discomfort of wearing the exoskeleton, no?
Discomfort or actually injury.
Injury.
Yes.
Okay.
If the motor's too powerful.
This requires more researching. It's important to research in this field because it's important to make the exoskeleton a helping tool. Okay. For example, one way to avoid the risk of injury is to make like a cushion in the chest. For example, in the active exoskeleton is a leg, so we could investigate how to include a cushion in the leg. Okay, so as the exoskeleton doesn't injure the leg of the people. For example, in passive exoskeleton, the Laevo exoskeleton has in the chest, it has a surface, okay, but it's a very big and heavy surface. So I propose to make a cushion in this zone because if the cushion is not included, the uncomfortability of the person wearing the exoskeleton could be damaged. Okay. Another ways to reduce the the risk to injury. For example, include sensors to control the movement, the power of the motor, and if the person is perceiving like pain, it can activate it can push an activator, for example, and the power and the motor, the engine reduces the power. Okay, this is the way I think of.
Okay, never mind the alarm. Farah, did you want to ask something? I see your mic's on.
No, I'm fine, thank you.
Okay, then thank you very much, Kirama.
Forget to wash your hands.
Thank you to your questions.
Thank you very much.
No,
So
it's for your I trust you. It's for your.
we finish now with the questions and answers, and now it's time for the judges to deliberate. So we will take 30 minutes, and we will be back at 20 to 6. If you can be a little bit before, that will be great.
Yeah. Okay.
So 30 minutes.
Now we'll move into the judges' deliberation forum, which is a separate forum then.
Excellent. Thank you.
And for those of you who want to stay, I'll be playing some more videos.
Thank you, Alan.
Hello, I'm Dr. Jem Baxter, and I'm Chief Engineer at the Institution of Mechanical Engineers. And I'm here today with our new president, Terry Spall, to find out a little bit about Terry and what his plans are for the institution. So thank you, Terry, for joining me today. And I'd just like to say congratulations on your new position. So we've known for a little while that you would become president after the elections this year. But could you perhaps tell our members a little bit about why you decided to put yourself forward for this role?
Of course, Jen, yes. I mean, like many members, I've been involved with the institution right throughout my career from graduation. So for me, that's kind of 40 years, just over 40 years. And I've always been very proud and passionate about the fact that I've been involved with the institution. And to be honest, as I've got more involved, then the sort of escalation to presidency has been one of the things that I've always aspired to. So I always had my eye on the role, and it's great to finally be here. But I think coming in at this particular time, it's a very interesting time for the institutions, a lot of change happening. And I think that my sort of personal characteristics play well to that, to get us through a period of change. I think I'm very focused on achieving goals and getting tasks completed. So I'm a very driven individual, but that's balanced by the ability to compromise and to reach a consensus. So I think as we've been going through a transition with the institutions, I've been involved for the last year. I think it plays well to my strengths, and I think that's one of the things that's really attracted me into this role, really.
Thanks, Terry. So some of our members will know you really well, and others may not know you so well. Would you be able to give us a brief outline of your career as an engineer and how you finally ended up in your current position?
I certainly can. I mean, I graduated in 1985, obviously in mechanical engineering, and I've spent my whole career in the automotive industry, working for a variety of companies. So first off, working for vehicle manufacturers up in the northwest with Leyland, down with Nissan at Cranfield, with Leyland Vans in Birmingham, and then I moved to Myra, and I spent a good deal of my career working for Myra. So many people know it previously as the Motor Industry Research Association, but its correct name today is actually Hariba Myra. So we're part of the Hariba group based in Japan. And it's been a fascinating company to work for. I am a development engineer by background, so I help to develop cars. And with my time at Myra, it's allowed me to sort of to broaden my role into a much more commercial role. Running international operation, in fact, setting up international operations for Myra in many countries, including China, Korea, India, and places like Japan as well. But also then broadening out into commercial activities such as selling. And then over the last 10 years, I've been working on their technology part development, which again has taken me into a completely different arena altogether. So many different roles. I think many people in the automotive industry will know me. Outside that industry, probably not, but hopefully as my time as president, I'll get to know many more of our members across not just the UK, but across the world.
Sounds like an interesting back catalogue of activities. So a lot of our members will know that each of our presidents comes into their position with an idea for the theme for their year. Can you tell us about what theme you've chosen and why you've chosen it?
I think that the choice will probably be obvious when I tell you, but I'm going to focus on future mobility. So the automotive industry over the last 10 years has been going through quite a metamorphosis as we've been decarbonising personal transport in a fairly significant way. You know, and not just decarbonising, but there's many sort of let's call them global megatrends that have been occurring that have had quite a profound effect on the automobile industry. So the fact that more people now live in cities, the fact that we're now digitally connected, the fact that you know, we have to decarbonise. So lots of things have forced the industry to change, and I think over the next 10 years we're going to see even more change. You know, even considering the fact we've now got to deal with the COVID situation, how that plays out and the impacts that will have, and it will have impacts. You know, we are going through an unprecedented change. So I thought it'd be quite interesting, really, to focus on the future of mobility. My presidential address will look at how that's going to play out. So what is going to happen over the next 10 to 20 years, and what can we expect by when? I think it's quite an exciting time. It'll be quite an interesting story to tell. And I've been to many presentations where people talk on this subject, and it is, if you're an automobile engineer, or even if you're not, it is an interesting subject because we all drive cars. We all use them to get around. So how it's going to change over the years now is going to be really interesting. I think if we can bring that down to the realist possible image we can of what's going to happen and when it's going to happen and what it's going to look like, then I think that'd be quite an interesting story to tell. So that's going to be the theme of my address, and certainly be one of the key themes I'll have through my year as president.
So that's a really big and challenging subject. And you did mention there both climate change and COVID-19. And there are the possibilities that we might experience some conflicts between those two particular issues. One being that perhaps fewer people may want to use public transport because of COVID-19, and we might see an increase perhaps in the use of private cars, which is something that's maybe a little bit undesirable. Do you think that that will actually be a challenge for the future of mobility, or will it begin to resolve as we understand more about coronavirus?
I'd like to think it would resolve. I mean, the obvious answer is that there's a lot of unknowns around at the moment, and I think people, if you're not, it's easy to overreact to the situation and then start thinking about extremes. You know, I think we have to allow this situation to play out. I mean, it is absolutely unprecedented, as we know. It's had a profound effect on everybody, really, not just in the UK, but across the world. And certainly, you know, my car's been parked in the garage for quite a few weeks now, and it will be coming out soon, I hope. But, you know, as we come out of COVID, then I think the way people will go through their daily lives will change as a consequence. I think we've all realised now that, you know, we can work virtually quite effectively, and in some cases you can get more done by sitting at home with your computer than you can by running around between different places. So the need to travel around might change as well. So there are lots of things that are going to play out, but I would like to see us sort of emerge out through this before we see sort of big decisions taken, because it would be pure speculation, I think, to go too far at this stage on what the actual outcome is going to be and its actual impact on the industry.
Thanks, Terry. So you get to have 1 year as the president of the Institution of Mechanical Engineers, and 1 year is not a very long time. And we know that following on from the reviews that we had in 2018 and 19 around governance and finance, that there is the possibility that more members are going to want to become involved with IMechE's activities. What do you hope to achieve in your 1 year with our membership and the changes within the institution?
Okay, so you are correct. I mean, one year isn't a very long time. You get 1 year to build up for this. One of the changes that we're making is that period of build up will actually go to 2 years. So we'll end up with 2 deputy presidents. So lots of changes are being built in to make people more effective when they do get into these roles, to give you a better chance. But I spent the whole year working on the reviews and implementing the recommendations that have come out of those reviews, working with a really great team of people who have gone to great lengths to really make sure that we understand the changes that need to be made, that we consult far and wide inside the institution and also outside the institution to make sure that we've got it right, and then to start to roll out those solutions It's been a massive task, and a lot of the membership probably haven't seen, maybe not even heard of it, but trust me, a huge amount of work's been going on behind the scenes, and they will start to hear an awful lot more about it over the next few months as we start to go more public with the actual transition that we're making. And it's fair to say that the process has been very consultative. So certainly within all the active parts of the membership, we've seen a lot of interaction, a lot of consultation, a lot of adaptation to change the solutions to things that are more acceptable to people. So a lot of that work's been done, and I hope as well as we go forward that will extend to the wider membership. So there are certain questions that we have that we'd like broad member input on as to how they'd like to see their institution change in the future. So we will be consulting with wider membership, as indeed we did at the start of the recommendations. So lots of things are going to change. It's going to be certainly a busy year, an unusual year, I guess, really, because it's not, the last time this was done was 20 years ago. And the changes that were made then have held up well for those 20 years. But it is time for change, very clearly. And I'm looking forward to playing a very active role in trying to make that happen.
That's great, thank you. And we mentioned a little bit before that we are living through some really quite unusual times. And for you coming in as president of the institution during a time when One Birdcage Walk itself is actually closed must be quite challenging for you. So do you have a message that you would like to share with our members?
Yes, I think we're all sort of wondering how this is all going to play out, really. It's very unusual to be kind of locked out of the One Birdcage Walk for so long, but that's the reality. That's what we're faced with. So I'd say to our members, just because the HQ is kind of shut down, it doesn't mean to say it's not operating. It is. The teams are very busy. A significant number of people now working from home. So many of the services that we offer, it's still business as usual, and the IMechE is operating. So do continue to engage. I think some people are probably worried about their jobs because they've been furloughed or even made redundant. But even in that sort of extreme situation, I think the institution has a role to play. So your membership of the institution is something that is probably even more important at times like that than at any other time, as you want to then present yourselves to potentially new employers. So don't give up on your membership. Do engage with the institution. And I'd also say, with more people working at home, perhaps it's also a chance to engage more with your local IMechE teams. And we're doing quite a lot of work, which you'll see the benefit of soon, as to how we can make it easier for people to engage locally with areas of technical focus that they're interested in, or if it's just more of a social thing where they want to meet other like-minded engineers. So there are lots of things happening. So my message is, engage as much as you can with what's going on.
Thank you, Terry. This has been a really interesting conversation, and I'm pretty excited about some of the plans for the institution, and you have a fantastic theme which will keep us all interested throughout the year. So it's my privilege to wish you all the best in your premiership, and to say thank you to everyone who has been listening and watching today. And I hope that they will all join us again soon for another episode of IMechE TV. Goodbye.
Thank you. Bye-bye.
Hello and welcome to this episode of IMechE TV. My name's Dr. Jen Baxter and I am the Chief Engineer at the Institution of Mechanical Engineers. And I'm here today with Dr. Tim Fox, who is Chair of our Process Industries Division and also one of the main authors of a report that we released last year on sea level rises. So thank you, Tim, for being here and taking the time to talk to us. Can you tell us a little bit about the report that you produced last year?
Yes, of course, and thank you for having me on the show. It's a real pleasure to be here. The first thing to understand is that sea level isn't an absolute, that over geological time, sea level rises and falls with the variations in the amount of ice that's on the planet. So as the ice freezes, sea level goes down, and as the ice thaws, sea level goes up. And that's a perfectly normal natural cycle, and we've been experiencing that for millions of years. So we're sitting in an interglacial at the moment between two ice ages, and sea level during that period appears to be absolute. But of course, we're now in a slightly different epoch in that the effects of global warming and climate change mean that potentially the amount of frozen ice on the planet is going to change quite dramatically in the coming centuries, indeed potentially in the coming decades. And that'll mean that we might see some significant changes of sea level during the lifetime of a lot of the infrastructure and engineered buildings, etc., that we construct and operate, maintain, and decommission. So we're entering a new epoch where potentially we as engineers have to deal with a completely different set of design criteria, where sea level might change significantly instead of remaining stable over that period of time. So that's essentially the background to the work that we did.
Thanks, Tim. And I know that you produced this with other members of the institution. And can you tell me a bit about the decision-making process? Why did you and other members feel that this was something that the institution should tackle?
Yes, so there's about a year and a half ago, we became, myself and some other members in particular, became aware of an emerging body of work, emerging body of evidence from around the world, from very reputable organizations that was beginning to indicate that sea level might rise quite significantly more than the International Panel on Climate Change has been projecting. So the current worst case scenario from the IPCC is a sea level rise of about 1 meter over the course of the century, which in itself is quite significant. Particularly organizations involved with studying the polar ice caps have been indicating that sea level rise might be significantly underestimated. For example, the North American Organization for Atmosphere has been indicating that the sea level rise might be as high as 2.7 meters by the end of the century. So the sea level rise will largely come from melting of the sea ice in Antarctica and Greenland. So we came together, myself and Frank Mills, to set up a project to collaborate on going through an initial scoping exercise of trying to understand how, as a profession, we should approach this challenge. And the work was funded by the Technology Strategy Board of the Institution of Mechanical Engineers, and it involved not only members of our boards, but also we brought in other boards from across the institution. And indeed, we engaged our technical centres overseas, including the India Technical Centre of the Process Industries Division in India, to get a global perspective.
And it is a process, isn't it? When you produce a report like this at the institution, we have to go through a number of different tasks in order to come to a final result. So can you tell me what you did in order to get the data that you needed to understand what was going on in those different areas, and how you actually formulated the report itself? And did you find out anything that was unexpected in that process?
Yes, so as you say, Jen, there's quite a significant process involved in coming to the point at which we can publish one of these reports. The first thing we have to do, of course, is identify the areas of knowledge that we don't have within our profession, and seek external help for that. So to provide a robust evidence base for that, we enlisted the help of John Englander, who's a internationally recognized expert on sea level rise based in Florida in the United States. So we engaged the Power Industries Division, and we engaged organizations outside the institution, including MRS, the Institution of Marine Engineers, Scientists and Technologists, and the chemical engineers and others in our sister organizations to come together to bring their perspective to the table as well. So then, to go through a process of evidence gathering, we undertook and facilitated a large number of workshops, both in the UK and in India, to solicit reaction to the challenge that was laid out by our sea level rise experts. So in the end, you end up with a report that truly does represent the engineering profession, or the IMechE, the mechanical engineering profession's response to this challenge in the context of the challenge laid out by the experts that we enlisted to help.
So some of the findings in the report were quite frightening. You know, a sea level rise of almost 3 meters is quite significant. So from your personal perspective and your experience of going through this process, what do you see as the biggest challenge for us as engineers as the sea levels do rise?
So the absolutely biggest challenge that we discovered, Jen, was that it really sits within the uncertainty of the instability of the ice sheets in Antarctica and Greenland. So the mechanisms are very poorly understood as to how and when these ice sheets might begin to collapse and lead to fairly large and significant rises in sea level. And that causes us as engineers a great deal of challenges and problems around how to design for that degree of uncertainty. We've been so conditioned to design within fairly certain boundary conditions and fairly certain data envelopes that all our design methodologies are based on historical backward-looking data that seeks to define parameters that are stable. But of course, this uncertainty presents us with a real challenge, and how we resolve the tension between that uncertainty and the economic impact of the decisions we're making. So if we decide, for example, to design a seawall 1 meter higher to allow for this potential sea level rise, then that has obviously significant economic effects in terms of the cost of the seawall, the return on the investment over what timescale, et cetera, et cetera. And of course, it's very difficult to find a route through that tension. So that's the key nub of the challenge for us as engineers, is the uncertainty rooted in that instability in Antarctica and Greenland.
And I guess that the report's recommendations built on that sort of fundamental area. So can you tell us what the key recommendations from the report were?
Yes, so we made 3 recommendations in the report, Jen. And the first one was a call to the government to recognise the emerging and increasing evidence base that sea level may potentially rise by a significant amount more than has previously been anticipated. The second was recommendation was an extension of that to ask that government takes potentially significant levels of sea level rise into account when developing strategies for dealing with climate change and climate change adaptation, and to account for the fact that this will have a significant impact not only on the built environment, but also on the industrial infrastructure of the UK. And then the third recommendation was government to set up a task force, which brings the professional engineering bodies, like the Institution of Mechanical Engineers, into a group that looks at these challenges in much greater detail, recognizing that our study was only an initial scoping study, and develops pathways to adaptation that meet all of the environmental, economic, and environmental considerations to find sustainable adaptation pathways.
So there's some strong recommendations there, and this is where the biggest challenge comes, isn't it? Taking those recommendations and driving them through government's policy and making those changes. So my final question really to you, Tim, is what's next? What do we do next to ensure that those recommendations that we as an institution make are followed up by governments?
Yes, so actually, as part of the project, we were very cognizant of the fact that we would need to engage government and government agencies in taking our work forward. And as part of that, we engaged those departments and bodies in the actual work itself. So we had representatives from the Environment Agency and the Infrastructure Commission, etc., involved actually in the workshops that we undertook to begin that relationship and find a potential longer term route to taking the work forward. And that has indeed continued since the publication of the work. We've continued our engagement with the Environment Agency. They're very familiar with the work that we're doing, and we've been providing further input into their strategies and thinking. And we've been working with the National Infrastructure Commission and a body called the Infrastructure Operators Adaptation Forum that brings all of the UK's major infrastructure representatives from those companies together and organisations together. And we've been informing them of our work and looking to work with them going forward. So yeah, and of course that's where, as volunteers within the institution, it becomes somewhat challenging, because clearly there's a significant amount of volunteer work in producing the reports themselves, but it's a question then of sustaining that volunteer commitment and contribution through for the long haul in terms of the onward engagement with government. So that in itself is a challenge in the work that we do at the institution.
It is, but it's also, I think, our volunteers are one of our greatest strengths too. So being able to access all of the knowledge in the way that you did has really demonstrated some great recommendations and some great follow-up to that as well. So thank you very much, Tim. It's been a really informative and insightful discussion. And I want to say thank you to everybody who has tuned in to either watch or listen to us talking today. And we hope to see you all again soon. So that's it from us. Goodbye.
Thank you very much. Goodbye.
My name is Claire Maycock. I'm the Business Development Manager for the Institution of Mechanical Engineers. The main thing that we are looking for when you apply for professional registration is that you are competent in the job that you do. Now, competence is the things that you do day to day, the jobs that you undertake, the training that you do, the experiences you have. And what we're looking for through that competence is that you can demonstrate that you are doing the things that you do correctly, safely, effectively, and most importantly, consistently. The competence standards are set by Engineering Council, and they're through a document called the UK Spec, which is the UK Standard for Professional Engineering Competence. Now, on the Developing Engineers programme, there is a competency chart that you can have a look at in reference to this that will give you a bit more information for all three of the grades, Eng Tech, iEng and CEng. So there are 5 competencies that you have to demonstrate in order to become professionally registered. Competence A is your knowledge and understanding, your technical knowledge and understanding, and competence B is your practical application. So those are your technical competencies. Now, what we're looking for in competence A is how you've extended your technical knowledge. You've perhaps been through university or college, HNC, HND, and in some way or form you will have extended, if it's work-based learning, formal training courses, learning from a mentor, visiting suppliers, all of those wonderful things are going to be a way in which you've extended your technical knowledge. And then you'll use that technical knowledge to optimize or manage a solution, a technical solution. Competence B, as I said, is the practical application, so problem solving. How do you identify a problem? Or you're given a problem, how do you go on to resolve, to design, to research, to come up with a solution? And put that into practice. And sometimes putting it into practice means it doesn't go out to market, or it isn't taken through because there isn't enough money or whatever it might be. That's absolutely fine. It doesn't necessarily make it a bad example. Competence C, we're starting to look at your leadership and your management responsibility. And that responsibility can be direct as well as indirect. So don't always think you have to have a team of 5 or 6 people reporting into you before you can be considered for application. Indirect responsibility is absolutely fine. So if you're managing projects and pulling different parts together, that is a way of demonstrating indirect leadership. Competence D is your communication and interpersonal skills. The reports you write, the meetings you attend, the emails you send, the telephone calls you have, along with your application paperwork and your professional interview, will all contribute to competence D. final competence is competence E, which is commitment to professional standards. Now, this is broken down into 5 sections, so it's probably the largest in terms of sections. But what we're looking for here, firstly, is that you have read, understand, and agree to abide by the IMechE Code of Conduct. We're also looking at health and safety. Now, health and safety, it's not about the PPE and making sure you're wearing the right equipment. It's about the safety procedures that you perhaps put in place to minimize issues, accidents, whatever it might be. We've got sustainability, the environment. What are you doing in terms of that? And
I can see you're back, Raymond.
Yes, we're back, all of us.
Okay, excellent.
For you.
We're here.
Do we have our participants here with us as well? Nicolas, Nassar, Thomas, Guillermo?
Yes.
Yes.
I am. Yes, I'm here.
Okay.
Okay. Well, I think it's fair to say that the competition was a high level. I would have expected no less. The marks were close, but the judges are in absolute agreement. And if I may, to keep it interesting, I'll give you the second place first and then the first place. So the runner-up this year is Nassar Avada. Well done.
Oh, thank you, judges and anyone that
thank you. Well done.
I guess
Well
everyone
done.
is allowed to unmute their microphone to give a round of applause, right?
Yes, thank you. I appreciate it.
Well done. And the winner is Nicholas Sammut from Malta.
Thanks.
Congratulations.
Thanks a lot. Thank you so much. And well done to everyone.
Congratulations.
Thank you.
Congratulations, Nicholas. As I say again, a very high standard. You've all done well, and it was all fairly close, but the decision was quite clear, so we're very happy to announce it. And thank you to my fellow judges also for a very good job done. And of course to Chema and to Adam for organising this.
Thank you.
Yeah, my pleasure. Thank you.
Well done.
Thanks a lot again, everyone. Thank you so much.
Now, normally at this stage, we all get together on stage and have a photo, but I don't know quite how you're going to run that one, Chema.
I think Adam was going to take a picture. I don't know if we have to switch on all our cameras and Adam, you can take a group picture, or how were you thinking?
I can try.